It's my pleasure to introduce Jun Zhang, who's going to talk about quantitative contact big fiber.
Many thanks for the invitation, and I've been enjoying staying here. This talk is based on joint work with Igor Uljarevic. It's a recent paper posted to arXiv. So let me start with something background of contact Hamiltonian dynamics, and also take the chance to introduce some notations. So M is a contact manifold. So in this talk, the contact manifold is always a boundary of a Liouville domain. So you have a function with time dependent on this manifold. You can get a vector field. It's called Hamiltonian vector field by solving the following two differential equations: alpha x h. Well, our convention is minus h, and iota x h d alpha. So dh minus dh act on the root vector field alpha. And once you have this vector field, you integrate this vector field, get a flow by ht for contact isotopy. So contact isotopy preserve a contact structure, but not necessarily contact form. So there'll be a rescaling factor there. And anytime one map of this contact isotopy will give you put together will give you a group. Usually define this as a count 0. And similarly, you can define the universal cover of that. Okay, and we call this H, or phi ht strict. With respect to alpha, if dh r alpha is equal to 0. So it means that this H function is a Reed invariant. This implies that the rescaling factor we usually write this as alpha ht. So in particular, if you run this process by inputting h is a constant function, then the vector field you get is some rescaling of the root vector field, and the flow you get is some rescaled root field. So you can think that the contact Hamiltonian dynamics is a generalization of the root dynamics. Okay, and okay, so you can on the level of functions you can play with the function in different ways. For example, if you have one Hamiltonian function, another Hamiltonian function, you can sharpen them together. And we will see the formula for that in a minute. But what's special about that is generate the composition of two contact isotopes. You can also do the same thing, like introduce notation H bullet G. It's actually simpler than that. What's generated is a concatenation of two contact isotopes. You do this first, and then you compose with this concatenation. So the one that I will be interested in this talk is bracket HG. Well, by definition, this is similar to the Poisson bracket in symplectic geometry. So the definition is dh first acts on the vector field generated by G. So if you are in symplectic case, this will be just the G of minus. This will be one term. But in contact case, there's another term, minus dg f of alpha and h. This is called contact Poisson bracket. By using this notation, see that the one that we talk about is strict. H is strict. If I know if you want to use this notation, it will be 1 H. H1 is 0. Now, the reason why I introduced this notation is because of following definition. So let's see, F is a map from a contact manifold to Rn. Write out the components. So F is F1 to F factor n. This alpha involutive. If now you have n many functions here, and the alpha involutive means that not only is n many function, you can also put 1, this constant function, f1, n pairwise also community. With respect to this bracket. And later we'll see that this one here will be essential. Notice that if each of these Fi's Poisson community is one, by what we just talked about, this means that each of these Fi is strict. And also that Fi and Fj are Poisson community. I should give you some example of how you cook up some alpha evolutive system. Let's take probably one of the easiest examples, S2n plus 1, and the standard contact structure. This is actually is a contact Polterovich manifold, effectively acted by the group torus n plus 1. Then you have this moment map F from S2n plus 1 goes to R n plus 1. N plus 1. So here, n plus 1 should view this as like the dual of the algebra of this group. Okay, and formula is easier. Formula is Z1 goes Zn plus 1 goes to norm of Z1 squared to norm of Zn plus 1 squared. Or if you're writing this square polar coordinate, it will be rho 1 to rho n plus 1. So obviously, each one of them are strict because the Ricks dynamics is just rotation of theta. So each one of the rho will be independent of theta. And also, you can check that the square J square. So you can check that the contact vector field generated by each one of this function will be, again, the rotation at the theta direction. So again, this will be rho, this will be theta. The Hamiltonian vector field is theta, so it's z. So this implies that the moment map I have F is alpha standing. But so there's not really nothing special about this example. I just put a remark here that this is actually a very cute fact in contact geometry. Consider the fiber of this map. Each fiber is actually displaceable. It's displaceable. It's essentially because the contact morphism does not preserve the bond. So this is not a constant map. So the preimage must be missing some small thing here. Then you use a rescaling to push everything to the small things. So it's pretty. But let me point out another example that is slightly more non-trivial. This is a famous one. It's called Ustalovsky's field. Let's see of dimensions. Plus 1. So I'll use the Briscoe manifold notation to write this. So sigma p to m plus 1 manifold is 2m plus 2. Notice that this is a real dimension of 4m plus 4. So to get to here, you have to cut down 3 dimensions. So one condition is normal that has to be 1. So it's cut down real one dimension. And then you have a complex polynomial, z0p plus z squared plus z2m plus 1 squared is equal to. So this cut down another 2 dimensions. And also we have this standard contact structure given by this contact form alpha p. So standard z0 d z0r minus 0.5. The rest of it is the same, just to change p. It's coherent to the power here. Okay, and then I'm wondering that how could I cook up some involutive map here? And this one is not a toric, so it's a little bit hard to do that. But unfortunately, around 2015, the 2 persons provided the answer for that. Uljarevic-Varolgunes, 2015. This is B draw, this is V draw. So they give the answer. The answer, if you consider map from this sphere to R m plus 1 by just using their notation G1 to G H, where GKZ is A to R, Z to J plus 1, minus A to J, Z to J plus 1. So this is for G. And H is, so here is I just pick one H, they actually a multiple choice of it. Z2 square minus this square. Wait, if you check that, go back to the definition, check this. Now this actually is alpha P invariant. And be consistent with the previous presentation, there's a remark here. So the remark here is not every fiber is displaced. This actually come from the main theorem. And when we state the main theorem, you will see why is it. Then you, for those who probably know this example and also know this example, there's a essential difference. And you distinguish them by you symplectic geometry, we distinguish by symplectic homology. So let me see. I believe everyone knows symplectic homology, so I just say a few words about that. Let me draw a picture. I haven't drawn the same picture. So we have my R. So here in this picture, I can see my W. So R is 1, my W is here. W. So I consider the a family of symplectic Hamiltonian function. Function on the completion. This is HA. So where's my what's my HA? You see too small here. Here in my W, and when you pass R is 1, you will be linear. With the slope, A is positive. Okay, and then there's a couple of things we can write here. So, for example, the Hamiltonian Floer homology on the completion with this Hamiltonian function HA is well defined by the maximum principle. Okay. Now, this is not compact case, so it's not certainly not trivial. Second thing is if HA is smaller than HB, which is more or less the slope A is smaller than B, then there exists a well-defined Floer continuation from H by HA, presumably HA, to the HF HB. And the last thing is the basic definition of symplectic homology. W is the direct limit. A goes to infinity, HF, HA. So there's a couple of ways to define the symplectic homology, and this way is usually called the turbo construction of symplectic homology. Okay, so let me put a small remark here. So the entire construction can be localized. Localize this construction near a subset. Okay, and this K can be even in a closed symplectic manner. So here we do everything on the Liouville domain on completion, and you can also localize everything on and you're subsetting even closed symplectic manifold. And this will give you something called a symplectic homology with convex symmetry. The notation is like SH M. So this is a machinery that was invented by Varolgunes around 2020. Okay, so we have a global definition and a local definition. About computation, symplectic homology is well known to be very hard to compute. I'll give you some examples of how to compute this. So the first example is done by Amy Smith. It says that every Liouville domain W such that the boundary of that is a stand sphere we just talked about, where it has at least one, the dimension at least three, well, has a symplectic homology vanished. Okay. And on the contrary, for this Ostrowski sphere, so this sphere admits a Liouville field W such that you can guess a symplectic homology non-zero. So in this way, you actually these two cases. But now let me state the main theorem. All right, so the main theorem was so this is one that I proved with Uljarevic. And also before that, like 1 week before our paper was to archive, there's another paper written by Sun, again, Uljarevic. So his name will appear many times in this one. And Varolgunes. And they also proved the same thing, 2005. Okay, so what's the theorem says? The theorem says the following. And again, so this is contact manifold as a boundary of a Liouville domain such that symplectic homology is not zero. Okay, and if you give me alpha involutive, the one that we find the beginning of the then this F has at least one non-displaceable fiber. And here, non-displaceable means that it's non-displaceable by an element in the non-zero.
Sorry, is it easy to see that the Briscoe construction is smoothly as one? Like we're trying to distinguish the contact structure, right? But the sigma P222, that's homeomorphic or diffeomorphic to S2 plus 1.
So it's a period, right? It's intersect with
Similar means that some Briscoe manifolds are actually exotic spheres.
yeah, right.
So this is like a standard one.
Yes,
This is a standard.
standard one, right? Well, so let's see as a comparison. So this type of theorem is not a pure cycle first. We still have some analog in symplectic geometry. It's true that around 2006, Entov-Polterovich proved the Floer version, which will be very similar to this. So X omega is a symplectic method plus closed symplectic. And if F is involutive, now this time is really the one that you feel. This involutive means that each of the component in this function is also convoluted with symplectic Poisson bracket. There's no one appears there. Involutive, then again the same conclusions that F has non-displaceable. And here here I'm see that I was informed by Igor that in the pre-quantization case, do I need to write down? Or I just say that in pre-quantization case, right, they can also with the condition that symplectic homology is not zero, then they also get the same conclusion.
Replacement of symplectic.
Good. And okay, so here's really remarkable. What is as you can tell that from the standard sphere it does not work, right? Because of the first you have already seen the fact that each fiber is displaceable, and the condition actually fails for the standard sphere because symplectic homology is matched. So symplectic homology non-zero is very crucial for this theorem. And also the important thing about the definition of alpha involutive, that one commutes with any others. So it means that any of its component needs to be strict is also necessary. Component function. Right. Strict. So both of them are necessary for the theorem. So I will leave this for you if you want to think about that. There will be some very easy example show that if this fails, then the theorem actually fails. I'll probably tell you at the end of the talk. Okay, and then the last remark is so there are two groups prove that. So our proof is based on the machinery that we developed this called contact Hamiltonian Floer homology. Not contact homology, contact Hamiltonian Floer. And the proof from SUV is based on the symplectic homology with complex solo SH. And it's not very surprising because the Varolgunes is actually in the okay, so let me see a little bit about what this theory machinery is. So I'll probably just tell you directly how to construct that. So here's our contact manifold thing. Then we will contact component function as defined the contact Hamiltonian Floer homology for this H is equal to the this is a symplectic version of Hamiltonian Floer homology. So it's defined on the completion, but the Hamiltonian function is this capital H with small h, where capital H is any function on the completion such that it will be in the form of R times H C when R is sufficient large. In the meterable construction, here H is not a function, H is a constant A. So it goes to all the way like this. So here is the generalization of meterable construction. So then we need to say a few things, right? So first, this is well defined. So in the meterable construction, everyone can actually work out this by the standard maximum principle. But for this case, it's slightly more complicated. So it turns out we're married, and again, it's with Uljarevic. We work out this maximum principle for this case, and around 2017 or while ago, maximum principle. And also, if H is smaller than G, even time-wise, of M. Now there exists again Floer continuation from the H. And the last thing is similar to symplectic model. If you actually make the H goes to infinity, with respect to this continuation method, what you get is standard symplectic. So what's the right perspective to view this? It should be generalization of Viterbo's construction, but it's in the intermediate step before you reach the symplectic homology. If you reach symplectic homology, there's nothing new. But here is really you stop there. You only study individually each one of them. Then you can use this homology machinery to see some Hamiltonian, contact Hamiltonian dynamics from this H. Right, so once we have that, I usually do this quantitative symplectic geometry. So we want to read off some numerical invariant from this theory. Now this time there is some trouble. The trouble is there's some ambiguity, right? There's some actually there's the freedom of your Hamiltonian capital H. Capital H. Look here we only need the eventually to become like linear in terms of H. We actually don't care about what's going on for the interior of W. Then this classic action field feature does not work very well. It's ambiguous. Like if you choose your capital H, my capital H, eventually it will give two different action functions, symplectic action function. Then the filtration is not the same. So here's a trick that how we can overcome this. The trick is fix this H, give you this H. Consider eta, a constant sharp H. Now this is a constant and sharp H. Now let's write out what's the formula of that. So it will first have eta. And then here, instead of, in general, we should put a conformal factor from the first dynamics, but here is eta is a vector. Real dynamics is strict, there's no conformal factor. The H itself composes phi, the dynamics getting from here is minus t. So this function generates the position by R alpha minus eta t composed with the phi ht. And you consider this function and also this Hamiltonian, contact Hamiltonian for homology of not H, but this function. So what looks a little bit surprising is that you want to study dynamics of H, but you won't study dynamics of H. You study the dynamics of H twisted by the Liouville. But there are two benefits. The first benefit is the definition of that eventually goes back to the standard symplectic homology, but on this on the completion and with the different choice of the H. Then in the standard symplectic homology Floer theory, you want to understand what is the geometric meaning of the fixed point of time one map. Usually it has some meaning. So what is the meaning of this? There is a meaning of that. Let's take a look at this. For example, let's take a look at symplecticization is my M. Eventually, in the completion, it looks like the symplecticization of that. But if you have the dynamics on M, that will lift the dynamics on symplecticization. And the formula is very explicit. We have Rx. So let's take this dynamics. This corresponds to this function. So you lift this dynamics as given a name of phi H eta t. The formula of that is R first divided by the conformal factor comes from this dynamics, but there's no conformal factor from here. It's just that we discussed phi ht of x. And the next component is just this one epsilon x. So it's a phi r alpha minus ft composes phi ht. Let us see what is the fixed point of type 1 map of that. Fixed point of type 1 map. Let's just write out what this is. It will be those points such that kappa h1 x is 1. There is no rescaling here. And also, should be a fixed point here. It's, if I write this phi h1x is equal to phi r alpha eta X. So this will be the fixed point of this. And look, if I write out this, you are writing out the definition of something that usually people know. It's precisely corresponding to the translated point of this phi h with the time shift. There's a time shift here. The translated point just means that it's not necessarily a fixed point, but it's a line on the same report. So it's do x first and it goes to somewhere, but it's actually can be reached by the reflow with time shift. Okay. So it's like it's not bad. Right? Fixed point of this is good, but it seems hard to fit into the story. But if you twist it, then again you can have some geometrically meaningful things for the fixed point. That's one thing, one benefit. The next benefit is it's a proposition that one can prove. If you assemble everything together, if you just keep doing this eta, if you put everything together, eta sharp h, all the r, and you have this eta lambda continuation method. We put everything together. This is actually form a persistence module. Over here parameters R. But what is new here is it's not the standard persistence module that R with the total order that A is smaller than B. It's a partial order that's really right this depending on H. It's a partial order, and let me just describe what the partial order is. So eta is smaller than this is oscillation of lambda. If I know if the eta is the same as lambda, or lambda minus eta has to be sufficiently large. So be bigger than the oscillation, which is defined as now this is not really like a Hofer oscillation, it's really the max. T, here's the max of ht minus the mean h. Okay, so first the persistence module can be defined only on partially ordered set. That's okay. Okay, so maybe I'm not right. Just say it. So persistence module can define on partially ordered set, and the general decomposition theorem, or the algebraic structure theorem of persistence module says any persistence module over a partial ordered set decompose into a direct sum of indecomposable persistence module over the partial ordered set. But unfortunately, this theorem does not say much, right? Does not tell you much information. And there's another theorem, corollary, says that if the partial order is totally ordered, like a standard R, then you actually can describe what the indecomposable persistence module is. It will identify with intervals. So that's where the barcode comes from. But unfortunately, this guy is not a total order. So from this perspective, it's a little bit hard to really extract like the barcode information from this persistence module. And let me, a couple of things I want to say, but first let me see that where does this partial order actually comes from? So the first remark is where the partial order comes from. It comes from the, in order to define this continuation map, the only way that I know how to define the continuation map, which I just erased, is we have to make sure that the first function is pointwise smaller than the second. So our first function is eta sharp h. Okay, by that, the definition is there. So I have to make sure that this is pointwise smaller than number sharp h, so that I will have a for homology of this guy to for homology of this guy. But this is the same thing to say that I have a formula here, right? So eta plus h composed with phi alpha minus ft smaller than lambda plus h composed with phi alpha minus lambda. So in order to make sure that this is guaranteed, right? So this lambda minus eta has to be bigger than something this minus this. And then that's where this the oscillation comes from. I don't think in general it's impossible. I think in general it's impossible to improve it because you actually don't know what's the value of H when it's moved by the reflow scale. So that's why you have the oscillation. Another remark is after we finish to do that, almost at the same time, Dylan Kent obtained a similar conclusion. Yeah, persistent module structure, if you send, they do exactly the same thing. But over the total of standard. But the difference is that the continuation map is probably not the same. Different continuation. Okay. All right, so as I mentioned earlier, since you have this not a very nice persistent module structure, it's a little bit hard to extract the classic invariant from that, like barcode invariant. But there's some invariant you can define. Well, if you think a little bit, what's actually essentially difference is finite length bar is a little hard to extract out because you don't know that there's a gap there. So the intermediates, you don't know what's going on. But for some other invariant, like what I'm going to define is a spectrum invariant. That's the endpoint of the infinite length bar. That's something like almost homological visible. That also appears there. Here let me use an easy way to define that. So again, you have this setting, and let's say E is the unit of symplectic homology. And if I give you the Hamiltonian function, you can define the following spectrum invariant. I'll mention this minus sign of all the eta such that E lies this an image of homology from eta which goes to the symplectic map. So this map is just like so. This is the limit of the guy here. So and see by definition, if the symplectic bar is actually 0, then the identity, the unit is the same as 0. There's nothing you need to check here. It will be the infimum of empty set, which is infinity. Then there's just minus. Okay, so this is the spectrum invariant associated. This in classical language, it will be spectrum invariant associated with the unit. But there's some property you can prove. Assume this is not equal to 0. If 0 is always minus 0. So assume this is not 0. Then there's a couple of things you can prove as for the property of the spectrum invariant. Let me say that the first property is the spectrum invariant of a constant map is always constant, same constant. And here, constant map in contact geometry makes sense. The constant being the root flow. Is the first property. The second property is if you have a true Hamiltonian function. Second property is stability property. Now H of G are strict. Then you have the following import. So I have C alpha H, C alpha G is smaller than the max of H minus G over the it's manifold and bigger than the minimum of H minus G. zero bound also. We have a stability here. And the next one is a triangle inequality. Okay, so if H and G are strict, then the C alpha, which now this time is really like this new operation, bullet G, mentioned at the beginning of the talk, this give you the concatenation of the flow, is smaller than C alpha H plus C alpha G. And also we have another property for phi is strict, non-zero, strict. Then you have some invariant property, C alpha H opposes phi is the same as C alpha H for any H. And many others. And notice that I put a lot of strict here. Strict, here also strict. It doesn't mean that we only show things strict. We can prove something much more general. Let me show you how general this can be. So for two in general, the bound will not be as good as the one here. Bound here, the real bound is bound is 2 times max over T, and the max of HT minus minimum of G. Right? If you think about it, this bound is much worse than down there. But if both of them are strict, then we actually get a much better one. So for the triangle inequality, I also put strict here. But if it's not strict, let me write out the general formula for the triangle inequality. In general, you have that C H bullet G will be smaller than C alpha H plus C alpha G. And there's a error term that can be 4 times the max of the oscillation H and the oscillation. So this error term is there's no way that we are able to exclude it in the general case. But at some point, if you want to have a general triangle inequality without this term, there's some small trick that you can relabel C alpha tilde H by C alpha H plus 4 times the oscillation of H. Then you actually can show that this C alpha tilde satisfies a general triangle inequality. But there's both a positive perspective to do this and also negative perspective. Positive perspective is that you can have a real triangle inequality, but the bad thing is sometimes we want to use the C alpha descends to the not only the function level but descends to the universal couple. The C alpha descends, but this one does not. So that's a drawback if you do this. Okay, so that's something like background from the contact Hamiltonian Floer homology, and so far the only numerical invariant that we can read off from our machinery. Then it's time to prove. So the proof will be a little formal. There will be a list of couple of properties we can show, and then the proof will actually come from all these properties. But I want to take the chance that to introduce some new concept in contact geometry. So here's a proof. So 3 steps. Step 1. Okay, so consider a function zeta alpha from the smooth function of contact matrix R, defined by zeta alpha, which is modularization of the spectrum variant. So first you need to show that this is well defined, this always exists. Now once you do that, there's a couple of properties you can prove from the invariant, the spectrum invariant. Okay, so assuming the sigma homology is not unique, then one property you can prove. There will be sorry, be patient. There will be 6 properties you have to prove. So the first property is zeta alpha constant function 1 is 1. And this is come from the series. It's actually come from the first property here. 1. And then the second thing is if Chen G is strict, then you have a stability property for the zeta function. Zeta alpha h minus zeta alpha g smaller than the max of h minus g. Now this time is time independent and bigger or equal to minimum h minus g. Anyway, it's really nothing we will deep. We will use this. We will use monotonistic properties. If h is bigger than g, then this is actually this is bigger. The second property. So maybe I write here the third property. This is by 2. Third one is okay, if write slightly faster, hg is equal to 1h 1g 0. So that means that both hg are strict and also the Poisson commute, this contact Poisson bracket. Then we have zeta alpha f h plus g smaller or equal to zeta alpha h plus zeta alpha g. So we actually try to prove something stronger than this. It's not just this. There's another more advanced formula for that, but unfortunately we failed. There's some tricky thing that we at the end of talk I can explain that. But this is already enough for our group. This is actually come from Philly, besides this one. There's another one here. Is okay, so 5 is strict. Yeah, zeta alpha h proposed find the statement zeta alpha is h. I have 5, which is like this is really come from 4. This 5 is come from the definition come from this one. So zeta alpha s times h is statement s times zeta alpha h. This s is positive. And the last one is something is a little bit not trivial. Let's see, h has a strict with displaceable support. Then zeta alpha h is equal to, and in symplectic geometry, this is proved by the famous in symplectic geometry, Ostrom strip. So eventually, you want to show that anything, if you have a displaceable subset, and any function that is complex part inside this displaceable subset, the spectrum invariant is uniform bounded by constant that only depends on this subset. And if you do this homogenization, then this is uniform bounded and the h goes to infinity. It's actually k. K goes to infinity is 0. Okay, now this is a property you can prove. And now I want to take the chance that let's propose something from partial contact on the state. So function on the function space that satisfy 1 to 6. So this will be a contact analog of partial symplectic quantity states that was invented by the Entov-Polterovich. Okay, so this is step 1, that you cook up something like eventually partial contact quantity state. Go step 2. So starting from this zeta alpha, for any closed subset A in M, let's define some measurement how big this subset is from this tau alpha A is infimum all the value of zeta alpha H, but this H is from M to 0, 1 strict and also smooth, such that the H restrict on the A is constant. Then again, by the properties that we have, so let's see it's not zero. So what we can say about this property, let's see. First property A is tau alpha M. The entire manifold M is 1. Which is clear that this if it's entire manifold, then H restrict on entire manifold is 1, just function 1, constant function 1. The constant function 1 get is 1. So that should come from 1. And another property is if we have two subsets, one A containing B, this implies that tau alpha A is smaller than tau alpha B. So how do you get this? Again, you use this property too, but use the monotonicity of the property too. So one is H is bigger than G, then this value is bigger than this value. So it's by 2. Now 3 is a little bit not trivial. C is if you have a collection of subset A1 to M, let's see the collection of subset is alpha involutive. So what does it really mean? Is it something a new definition of a subset? Collection of subset is alpha involutive. It just means that there exists alpha involutive functions such that each of the AI is a predimension of some subset Ra, and F is involutive. So this so subset alpha involutive means that it's a predimension of alpha involutive. And then you can show that there's a sub-additivity problem. This tau alpha A1 union A, but smaller than tau alpha A1 plus tau alpha. But the last one is so this is okay. So this comes from so 3. The last one is okay. So A is a predimension alpha involutive. Alpha involutive. And it's displaced. And probably you guess what this means. So tau alpha A is basically this is called from 6. So once you have this A, B, C, D, and you oppose them, something for the contact quasi-measure. As a function of the connection of say connection of flow subset. Subsets of M. And it turns out you can by the continuity you can extend it to extend to the open subset, but we don't need in our program to 0, 1 function satisfying. I turns out we don't need the D actually satisfy A, B, C, D. So it will be another analog of quantitative measure, but not on the symplectic, but on the commutative. Okay. So once you have this step 2, now you actually can see that what's the one line. So I prove by positive. Suppose there's no big fiber. Every fiber is displaceable, so it means that there's a neighborhood that is displaceable. Suppose no A5. Then you can find this W with boundary M. But find a closed subset A1. So they exist A1 to A alpha invariant and displacement. And cover of that, or cover of the interior of that, is entire M. Now you finish the proof. So have tau alpha of M. By A is equal to 1. By this is equal to tau alpha of A1 union A. Then by sigma, small tau of A1 plus tau alpha of AK. And then by B, each one of them 0 to 0. So that's the end of it. Okay, so I think that's the end of the proof. I think that's the end of talk. Thanks.
Questions?
So I mean, these are actually invariants of the contact manifold with the filling.
Yes.
Do you expect any kind of invariance?
But this invariant under the its invariant is a strict contact morphism. But in general, that the spectral invariant is not really invariant for any contact morphism. Probably I wrote earlier that as a C alpha H. This is basically like invariant property. So this is not true for general alpha. If alpha has scaling factor, there will be some scaling factor. But if it's alpha is strictly, it's only 1.
Do you expect any independence of the shape of the invariants from the filling, except
So the role of the filling is a little weak to see. The role of the filling here is only provided the algebraic condition that it cannot be equal to 0. So then otherwise all the special here is special invariant here is minus infinity, so I cannot see much. There is some role, like I think in this SUV proof, we also need some something is not 0 come from this relative symmetric homology compact support. Their condition there is to guarantee that the subset is rigid enough. So it is a little bit hard to say what exactly the invariant of the domain is playing this. So this numerical data is come from dynamics, come from this transited points, not really come from the information of the Liouville domain itself.
More questions? If not, let's thanks Jun again.